Hi, my name is Paul. I worked as an engineer for about 37 years, and my job was to design and build digital logic systems for use in wireline and wireless phones. During that time, I also taught digital logic, Boolean algebra at the college level for about 8 years. In this video, I'm going to be discussing Boolean algebra and the minimization techniques used to define a minimal logic function. The goal is to use the minimized logic function to create logic designs which satisfy the requirements of the function as defined by the system you are designing. The whole goal is to get a minimized design so you can get lower power, less real estate, and less gates. Well, less gates is going to define as lower power. So anyway, hope you enjoy the video. Thank you. In this video, we're going to talk about Boolean algebra. The concept of Boolean algebra was developed by English mathematician George Boole back in 1847. His basic contribution was a set of laws and rules in mathematics which could be applied to problems of deductive logic, and hence Boolean algebra was born. But not until 1938 was there a practical application used for Boolean algebra. And that practical application was using Boolean algebra for analyzing the multi-contact networks for telephone switching systems. The first practical application of the algebra paved the way for use of Boolean algebra as a tool in logic design. What are we going to talk about in this video, and what's our goals? Well, we'd like to gain an understanding of the operators, laws, and rules of Boolean algebra. Secondly, we want to understand how to logically manipulate Boolean expressions using the laws and rules of Boolean algebra. And learn how to complement a Boolean expression using De Morgan's law. And we'll be talking about De Morgan's law, what it does, and how you can find a complement of a function. The whole goal of using Boolean algebra to minimize expressions is to generate a minimal implementation or a minimal solution. And because the minimal solution is going to contain fewer gates, and gates are going to be what's used to implement the Boolean expression, Boolean terms within the expression. And if you have fewer gates, when you're implementing a function in either a chip or a discrete breadboard or a discrete printer wiring board, you want to have a smaller footprint. You have a smaller footprint, you're going to have lower power. So if you have fewer gates, smaller footprint, you're going to have lower power, and thus a better design. You can get more gates on a single piece of silicon. We'll discuss that. Okay, let's get into Boolean algebra. There's 4 operators within Boolean algebra. These 4 operators are plus or union, intersection or multiplication, complementation, which is the how to inverse a function or find the inverse of a function, and equality. Okay, the union is not the normal union or normal sum that you'd find in normal algebra. It's not the modulo 2 sum. It's just a Boolean deductive logic sum. Let's look at a Venn diagram and show what 2 functional elements would look like in a Venn diagram. The U is the universal set of functions. A and B represent subsets within that function. So if we were to draw what A and B was within this universal set, it would be everything in A and everything in B. So you can see that the union or sum of A and B is equal to all the elements in A as well as all the elements in B. Okay? Now the intersect, or the multiplication of two functions, A and B, two subsets of the universal subset, is just this intersection of the two functions A and B. Everything that is common to A and B is called the intersect, and it's just this area right in the middle here. Complementation says that for function A, for set A, there is a not A which defines everything, or the complement of A, which defines everything that is not A. So A is in the gray area here. Whoop, let me get rid of that stuff here. A is in the gray area, that's everything in A. Everything that's not in A is the complement of A, or A naught. Okay? Inequality just says when A equals B, everything in A is included in B, and that's the A equal B. That's the unity operator. Okay, let's do some function examples, and I'd like to explain basically what a function is and what the structure is. A Boolean expression is written like this. You have a function, and in the brackets behind the function, you define what variables hold true are going to be in that particular function. For this particular case, we're going to have variables A, B, and C. So on the right side, you're only going to have variables A, B, and C appear, because this is the domain of this function, and the domain defines the variables that are going to be used. So within the Boolean expression, you're going to have terms, and here's one term. Includes A, B, or C, or any combination thereof. So this one has three terms. Now, each of these Boolean variables can have two values, either a 0 or a 1. Or you can call it, it's either true, if it equals a 1, and false if it equals a 0. Okay? Let's write another function. Let's do another function here. Let's make one up. So I got f of u, v, w equals u bar, vw. This is the intersect function, u times v times w, plus vw bar plus u w bar. Okay, so again, this is the function as we define it, and this is the domain of the function right here, and within the domain are the variables that are going to be used in that function. And for this case, we have variable u, variable v, and variable w. So on the right side, that's all you're going to see is u, v, and w. This is the first term, this is the second term, and this is the third term. So what we're going to find out is when we plot this function, or we look at this function, this is the area. These terms define where the function is going to be equal to a 1. And we'll talk about that. So let's do another one. F of A, big B, big C, big D. The domain of this function is 4 variables, A, B, C, D. And you're going to have terms that are written using these 4 variables. Now, I'm just making this up, so I have no idea what it is or anything, but it doesn't matter because I'm just showing you the structure of a function. So we're going to do A, B bar, that's our first term. Then we're going to do A, B bar, D plus C bar. Okay, so there's one term, there's another term, and then there's another term. So in each of these terms, you don't need all the variables. You can have a subset of those variables. You can have A or B, whatever you want. Okay, so this is another example of a function. Okay, now we're going to talk about the laws of Boolean algebra. And the first three that we're going to talk about, now we're going to talk about the laws of Boolean algebra. Commutativity is the same in Boolean algebra as it is in normal algebra. That is, x plus y equals y plus x. You can interchange x and y, the order of x and y, and you don't change the value of it. The same with you have x times y equals y times x. You can change the position of x and y, and it doesn't change the value of the function. This is the dual. Number 2 is the dual of number 1. The second one is called associativity. And what that says, if you have, for instance, in 3 here, you have x plus y, parentheses, plus z, that's equal to x plus y plus z. You can change the order of the parentheses. And typically, parentheses talks about what you do first. But with associativity, what this says is it doesn't matter whether you do that, x plus y first, or y plus z first. And the dual, again, is x times y times z equals x times y times z. Bracket, bracket. Okay? Distributivity says that, for instance, number 5, if you have x plus y times z, you have a mixture of plus and multiply, or union and intersect. That's equal to x plus y times x plus z. Now, the second one here is what we normally are used to using with normal algebra, and that's you just multiply this out. You get x times y plus x times z. Okay? So this is laws 5 and 6. Now, the final law we're going to talk about, number 7, is not true for normal algebra. This is a Boolean algebra unique function. And that says that anytime you have a variable and you complement it twice, it's just equal to that variable. And in fact, if you have a variable and you complement it an even number of times, n equals even, 2, 4, 6, 8, up to an even number, that's just still equal to x. If you take that same variable and you complement it if n times, and n is equals an odd number, then that variable comes out to be equal to x bar, or the complement of x. Okay, that's very useful for minimizing Boolean algebra expressions. Okay, now we're going to talk about the rules. This first rule is called union, and it describes how a variable combines both with literals like 0 and 1, and also intersects with 0 and 1. The first one is x plus 0 equals x. Now that's the same as in normal algebra. Let's try that. Let's verify that. Let's let x equal to 0. Let x equal 0. So we'll have 0 plus 0 equals 0. Well, if x was 0, okay, that's true. Let's let x equal be a 1. Let's let x be a 1. So in this case, we have 1 plus 0 equals 1. Okay, and 1 plus 0 is, in fact, if x is 1, then it's equal to x. So this is true for normal algebra. The second one is not. Let's let x equal 0. X equals 0. Okay, so we have 0 plus 1 equals 1. That's true. What if we have let x equal 1? So if x is 1, we have 1 plus 1 is equal to 1. Okay, that's not true. in normal algebra, because in normal algebra you're going to get a modulo 2 sum, which means you'll go 0, 1, and then to 10, like we talked about when we did number systems. So this is not a modulo 2 sum of 1 plus 1. This is a logical sum of 1 plus 1. So this is the variant right here. Okay, now let's talk about intersection. Intersection is how variables interact with the literal 0 and 1. So x times 0 is equal to 0. Well, we know that anything times 0 is always 0. X times 1 is just equal to x. Well, anything times 1 is equal to whatever that is. So we can see that this is true in normal algebra also. Okay, sameness. What sameness says is if we have x times x, that's equal to x. Well, in normal algebra, you'd have x times x equals x squared. Okay, but there's no squared function in Boolean algebra. There's only like single variables, non-exponentials. So x times x is equal to x. X plus x is equal to x. In fact, you can expand this out and say that x plus x plus x plus dot 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 x is equal to x. This whole thing would reduce down to a single x. Okay, that's very powerful. The criteria is that this has to be exactly the same. Okay, same variable or combination of variables. Okay, the same holds true for multiplication. If you have x times x dot 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 times x, that's just equal to x. Same thing. Okay, no such thing as x squared. Okay, what if we have something like a b bar plus AB bar? What's that going to be equal to? Well, the whole term, the sameness theorem, the sameness rule applies to the whole term. This is the term. If the terms are identical, AB bar is the same as AB bar, that's just going to be equal to AB bar. Let's do another one. A B bar C bar plus A B bar, B bar A B bar C bar. So again, that's just equal to, from the sameness theorem, A B bar C bar. Okay, this is a very powerful rule for use in minimization of Boolean expressions. You use this rule a lot. Okay, now let's talk about complementation. Anytime you have a variable and its complement multiplied or intersected together, that's equal to 0. So let's check that out. Let's let x equal 1. X equals 1, x bar equals 0. So we have 1 times 0. 1 times 0 is 0, okay? What if x is equal to 0? So x is equal to 0, x bar is equal to 1. 0 times 1 is 0, okay? So that's the same as normal algebra. Now, how about x plus x bar? Let's let x plus x bar equals 1. Let's let x equals 1 plus x bar is a 0. 1 plus 0 is 1, that's true. And how about if x is a 0? We'd have 0 plus x bar would be a 1. Equals a 1. Okay, that's true. All right. Let's go to the next one. Absorption. X plus x times y equals x. Not as obvious, okay. And the dual is x times x plus y equals x. So this one is, these two are not as obvious. So because they're not as obvious, let's go ahead and prove it. Prove this part right here. with the rules and laws that we've already discussed. Okay, so what are we going to prove here? We're going to prove that x plus xy, that's this part right here, is going to be equal to x. Okay, we want to prove that this part right here is equal to x. Well, the first thing we're going to do is we're going to multiply this times x plus x bar. Okay, and how did I know to do that? Well, I've done it before, I guess. And after you've done a few of these, you'll figure out what's the best way to do it. But anyway, I'm going to multiply by x plus x bar. But as you'll see that x plus x bar, if we look at x plus its complement, that's equal to 1. So x plus its complement is equal to 1. So this is equal to a 1. And then anything times 1, x plus x bar times 1. Okay, x times 1 is equal to x. Okay, so x plus xy times 1 is equal to x plus xy. So that's okay. So let's expand this out. And what are we going to get? We're going to get x times x. First term, x plus x and x bar plus x bar plus xxy plus x bar xy. Okay, well, let's look at these terms. Xx, from the sameness theorem, x times x, number 5 right here, it says that xx is just equal to x. I'm sorry, xx is just equal to x. So we have x plus x times x bar. Well, what's x times x bar? Anything times its complement is equal to 0. So this whole term here is a 0. So that's a 0. We don't have to include it. Xxy, well, from the sameness theorem, x times x is equal to x. So this is a single x times y plus x bar x, y. Well, what's x bar times x? X bar times x is equal to 0. So this whole thing is a 0. So what are we left with here? We're left with x plus xy. Okay, let's factor out an x. And we get 1 plus y. Okay, what's 1 plus y? 1 plus any variable. 1 plus any variable is just equal to 1. So this is 1. And what's x times any variable? X times 1 is just equal to x. So this is just equal to x. So with this manipulation right here, we're able to show that x plus x times y is equal to x. Okay? Let's do another one. Let's prove the second part of this one here. Let's prove this one right here. Prove that x times x plus y equals x. This one's probably a little easier to do, but let's verify it. Let's go ahead and expand this one here. So we're going to take x times x plus y, and we're going to multiply out the terms. We're going to get xx plus xy. We multiply the x times the y. So we can factor out xx is just equal to x. So we got x plus xy. Xx from the sameness is equal to x. So now we can factor out an x. And we get x times 1 plus y. And 1 plus anything variable is equal to 1. So from number 2 right there. So it's equal to 1. And any variable times 1 is equal to that variable. So it's equal to x. So we've taken x times x plus y, and we've proven that it's equal to x using the rules of Boolean algebra. Okay, let's talk about this next one here. This one here you use a lot too, and it's called, I call it no special name because I've never found a name for it. If any of you can find a name for it, that would be awesome, but I just call it no special name, and what it says is if you have a variable x plus its complement times another variable, that's just equal to the x times y. And the dual of that is x plus y. And the dual of that is x times, we're doing the intersection instead of the plus, x times, parentheses, x bar plus y is equal to xy. Okay? Okay, and what we're going to do this time is I'm going to take the right side of the expression and prove that it equals the left side of the expression. So I'm going to take x plus y, and I'm going to prove that it's equal to x plus x bar y by manipulating the Boolean expression using the Boolean rules. Okay, so again, I'm going to take this x plus y, and I'm going to multiply it by x plus x bar. Again, x plus x bar is equal to 1. Anything summed with its complement is equal to 1, rule 8. So that's equal to 1. And then anything times 1, any variable times 1 is just 1. And that's what this one right here, number 4. Okay, so let's expand this expression. So we're going to get xx plus xx bar plus xy plus x bar y. All right, from the sameness theorem, we know that that's just equal to x, so it's equal to x. Xx bar, anything times its complement, is just equal to 0, so that's a 0, so we don't have to include it. We have xy plus x bar y. Okay. So let's factor out an x here. We'll get an x times 1 plus y plus x bar y. And 1 plus y is just equal to 1. And any variable times 1 is equal to that variable. So we end up with x plus x bar y. So we've proven that x plus y is equal to x plus x bar y. Okay? Now let's talk about De Morgan's theorem. What De Morgan's theorem states that you can find the complement of a function by replacing each variable by its complement in that expression and interchanging all the plus operators with multiply operators and vice versa. Here's an example where we're going to use De Morgan's theorem. And so remember, De Morgan's theorem says you replace each variable by its complement and you interchange all the plus operators and multiplication operators and vice versa. Well, let's do this one here. So if we want to find the complement of this function, the function complement is equal to x plus y bar z. And take the complement. You have to complement the whole function over the complete expression. Okay, so what De Morgan's law says that is to remove this complement bar, you have to like complement each of the individual terms. Here's the first term, so we'll complement that. Okay, and then we'll complement this term. Well, what's the complement of y bar z? You have to complement the whole thing. This is, you complement the whole term, so we complement the y bar z. Okay, and we change the operator from a plus to a multiply. Okay? So now we notice we have a y bar. The goal is to get rid of the bar, okay? And have individual terms with their complements. So we have y bar z complemented, and that's going to equal just this piece right here. We complement this term. Y bar complemented is another bar over the top. We take this term, the second term, z, and we complement it, and then the multiply goes to a plus. So that's equal to y double bar is just equal to y plus z bar. So what do we have left here? We've got x bar plus y plus z bar. Okay? So that's the complement of this function right here. More generally, for De Morgan's theorem, if you have a function that's all the terms are multiplied together, term 1, x1, x2, x3, dot, 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 x to the n, you want to find the complement of it? You complement each individual term, x1, x2, plus x3, dot, 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 x to the n, and you change the operator, the operator in every case, from, in this case, from a multiply to a plus. Now, the rule is these have all got to be the same multiplications. Okay, they all got to be multiply, or they all got to be sum. They can't be a mix of multiply and sum. They got to be either one or the other. And rule 1 says they got to be all multiplication. Rule 2 says they got to be all sum. In other words, you couldn't have x1 times x2 plus x3. That wouldn't work. They've got to be all the same operator. Okay, so it's either going to be all multiply or all sum. Okay, this is a very powerful formula. Let's find the complement of function ABC. We've got AB bar plus AC plus AB bar C. All right, so we take the function equals AB bar plus AC bar plus A B bar C. We want to find the complement of it. Okay, so we'll complement the function, and we have to complement the total function right here. So we want to reduce this down using De Morgan's law to get down to single variables, either true or complemented. So let's do each individual term. We're going to get A, B bar. And again, they're all summed, so we can do it. It applies because they're all sum and they're not a mixture of sum and multiply. Okay, times, because this is going to change to a times. The next term is going to be A, C bar complemented. And then we'll bring down this plus to make it a multiply. And this is going to be A, B bar, C, the whole thing complicated. Not complicated, complemented. It is complicated. Okay, let's keep going. We're going to get rid of this bar because the idea is to get down to single variables, not two variables with a complement bar over the top. Okay, so this one right here is going to go to A bar. This is going to go to a plus. This is going to go to a B bar bar. Okay, so we just did this one, so we maintain everything else. So let's continue on here. We got the A. We're going to like double complement. I'm sorry, not double complement. We complement that individual variable, complement. And then this operator goes to plus. Toggles. And then we have C bar complemented because we have C bar. Okay. And then this times. We're going to do this one. We're going to get A bar. B bar, bar, because we already have the B bar, and we're going to put another bar on top of it. I'm going to break it up, and we have to put this as a plus. This multiply is going to go to a plus, and then this multiply is going to go to a plus. Plus C bar. Okay, let's rewrite this. A plus B double bar is equal to this B times A bar plus C double bar is a C, times A plus B double bar is a B plus B plus C bar. I'm sorry, A bar plus B plus C bar. Believe me, you miss one of those, the whole thing is messed up. Okay, so that's the final answer right there. Okay, the complement of this function right here is equal to this function right here. Okay, again, what does a complement mean? Well, if you look at a function, it's going to have its, we're going to talk about truth table, it's going to have values where it's 1 and values where it's 0, or values where the function is true and values where the function is false. If you have the complement of that, the previous values that were true for a 1 will now be 0. And the previous values for the uncomplemented version that were a 0 are going to now be a 1. So you can complement. It's like putting an inverter on the output. But anyway, it's a complement. Okay? Let's do an example here. Let's simplify this expression. F of A, B, C equals A bar BC plus ABC plus B bar. Okay? So, what are we going to do first? Well, let's factor out for this, from this first term, let's factor out a BC from these two terms right here. So we're going to get A bar plus A plus B bar. Okay. So A plus A bar, anything plus its complement is equal to 1. So this is a 1. And any variable or term with variables in it, BC, times 1 is equal to that variable BC. So this is just equal to BC plus B bar. So if we've got B bar plus BC, using this theorem right here, it's equal to B bar plus C. Okay, that's the final answer. All right, let's do another example. Let's complement this function here. So how are we going to complement it? Well, we're going to use De Morgan's theorem. So let's De Morganize this. So the function bar is equal to A bar B plus B C bar, and then the whole thing complemented. Okay, De Morgan's law says that we take each individual term, A bar, and we complement each individual variable. It's A bar, so we complement A bar as another complement, and we have a multiply there, so this becomes a plus, and then we have B bar, because you complement the B. Okay, I'm sorry. Let's rewind that. I'm going to do each individual term. See, I messed up. Okay, I'm going to complement each individual terms. So I'm going to get a bar B, complement, that's the first term. Change this to a multiply. And then we got B, C bar, complemented. Okay, now let's reduce each of these individual terms. We're going to get a bar, and then the complement of the a bar. This goes to a plus, and then we'll have b bar. So we've removed this complement bar. Okay, and that times, demorganize this function right here, and it becomes b bar. This goes to a plus, c bar, bar. Okay, so it's equal to a plus b bar times b bar plus c. Okay, let's multiply this out, and we're going to get all the terms. We're going to get a b bar plus AC plus b bar plus b bar c. Okay, we know b bar is just equal to b bar. Okay, so we're going to get, put it up here, we're going to get a b bar plus, I'm going to put this b bar next to it, plus b bar plus AC plus b bar c. So if we take factor out a b bar from here, we're going to get, I'll get rid of this here a little bit. Continue on. It's going to, so let me rewrite it here. It's going to be equal to a b bar plus b bar plus AC plus b bar c. So factoring out a b bar here, we get a plus 1 AC plus b bar c, and that's equal to b bar plus b bar c plus AC, but b bar plus b bar c is equal to, these two right here is equal to b bar times 1 plus c, which is just equal to b bar. So let me write the final answer up here. It's equal to b bar plus AC. I'm sorry, b bar plus AC, yes. Okay, so we say that the complement is equal to b bar plus AC, and the true is equal to a bar b plus b c bar. So let's look at something called a truth table. A truth table is a tabular sheet that looks at all the combinations for the variables that were within your function. In this case, we have variables a, b, and c. And if you have 3 binary variables, if you have 3 variables, you're going to get 2 to the 3 equals 8 combinations. So we're going to have 8 combinations, 0 through 7. So what we're going to do is we're going to look at each of these terms right here for the true function right here. And whenever this particular term is true, we're going to write a 1 in the truth table. Okay, so for a bar b, when a bar b is true, a bar means a is a 0 and b is a 1. So we have a is a 0 and b is a 1 right here. A is a 0 and b is a 1, a, b, c. And we have a is a 0, b is a 1. So for this particular term, it's defining two ones of the function. The second one is when b is a 1 and c is a 0. Okay, when b is a 1, well, we've already got that, so it's redundant, and c is a 0. B is a 1 and C is a 0 is right here. What about A? Well, you don't care about A. Just as in the AB portion, you don't care about C. So for a function, these are the ones of the function. Now for the inverse function, okay, we expect the inverse to be equal to 1 when this one's a 0. Okay, so let's do the inverse function. That's this one here, function bar. Okay, is equal to b bar plus ac. Okay, so it's going to be a 1 when b bar is a 0, when b is a 0. So when b is a 0, we have a 1 here because b is a 0. B is a 0 here, we have a 1 here. B is a 0 here, we have a 1. B is a 0, we have a 1. Okay, so 0, 0, 1, 1. So 0, 0, and we have a 1, 1. Okay? Plus, so the function is a 1, the complemented function is a 1 every time b bar is a 0. Or AC is a 1. AC is a 1 in this case right here. Okay? So what we've seen now then is this is the function 0, 0, 1, 1, 0, 0, 1, 0, and this is the complement of that function. We complemented it using De Morgan's law, and this is what we came up with: 1, 1, 0, 0, 1, 1, 0, 1. So it is the complement of whatever f is. Complement of 0 is 1 and vice versa. So the truth table proved that De Morgan's law worked for that particular reduction. Okay, in summary, we've talked about Boolean operators, laws, and rules, which define the relationship between the variables within an expression. Then we use the rules and laws to reduce expressions without changing the logical relationships, and that's important. You can't change the logical relationship, because if you do, you're going to change the value of that expression. Okay? But typically in practice, you don't use these rules because anything more than 3 variables, even 3 variables, it gets pretty complex to do reductions. And sometimes you'll have 4, 5, and even 6 variables. So most of the time in practical use, you don't use Boolean rules and laws to minimize expressions. You'll use other things such as Carnot maps, which will be described in the next chapter. Well, that's it. That's Boolean Algebra. We finished chapter 2. I hope you enjoyed the video. If you did, would you please subscribe? I'd love for you to subscribe to my video because it really helps the video. And also give me a thumbs up if you liked it. And also any comments will be appreciated. I'm working on chapter 3, which is going to be Carnot maps. So I'll look forward to producing that and then notifying you when it's available. So anyway, thanks again. I really appreciate it. Bye.